For years, the biggest names in technology seemed to control the future of quantum computing. Google, IBM, and Microsoft captured the headlines with bold announcements and billion-dollar investments. But while the world watched those giants compete, a research team at the University of Chicago quietly made a breakthrough that has scientists asking a surprising question. Have they discovered the smarter path instead of simply building a bigger machine? Why are experts calling this moment so important? What obstacle has kept quantum computers from reaching their true potential for decades? And why are some of the world's most powerful companies suddenly paying close attention? This isn't just a story about speed or size, it's about solving the problem everyone else struggled to overcome. To understand why this announcement shocked the industry, we have to go back to the biggest weakness every quantum computer has always faced. The excitement surrounding quantum computing didn't begin yesterday. Long before today's technology giants entered the race, physicists were already imagining machines that could solve problems beyond the reach of ordinary computers. As traditional chips became smaller and more powerful, engineers also discovered they were slowly approaching physical limits. Packing more transistors onto tiny circuits could no longer deliver endless leaps in performance. Quantum mechanics offered a completely different idea. Instead of bits that could only be 0 or 1, quantum computers would use qubits, which can exist in multiple states until measured. Imagine a light switch that isn't simply on or off, but can explore many possibilities before settling on one answer. That strange behavior promised enormous computing power. Scientists believed these machines might someday design new medicines, discover advanced materials, improve artificial intelligence, optimize global logistics, and crack mathematical problems that would take today's fastest supercomputers millions of years. Universities, government laboratories, and pioneering researchers laid the foundations before companies like Google, IBM, Microsoft, and ambitious startups poured billions into the field. Governments across the world launched national quantum programs, turning scientific curiosity into a global competition. Each announcement fueled bigger expectations, attracting investors, engineers, and young scientists eager to shape the future. Researchers predicted that practical quantum computers could transform finance, climate modeling, secure communications, and scientific discovery. Optimism spread across conferences, classrooms, boardrooms, and laboratories, convincing many that a computing revolution was only a few breakthroughs away, despite growing technical doubts. Decades of research produced remarkable milestones, from early theoretical ideas to increasingly capable experimental systems. Yet one challenge refused to disappear. Every promising result eventually ran into the same invisible barrier. The technology looked revolutionary on paper. Reality turned out to be much more difficult. Every new breakthrough created excitement, but every celebration ended the same way. That invisible barrier had a name: decoherence. Quantum information is incredibly fragile. The slightest vibration, tiny temperature change, stray electromagnetic signal, or interaction with the surrounding environment can disturb a qubit before it finishes a calculation. When that happens, useful information begins to disappear. Scientists call these unwanted disturbances noise. As more qubits work together, small errors do not stay small. They spread, combine, and multiply, making long calculations increasingly unreliable. This error accumulation became the greatest obstacle standing between exciting laboratory demonstrations and practical quantum computers. Building larger machines did not automatically solve the problem. In many cases, adding more qubits simply created more opportunities for mistakes. Keeping quantum processors stable required extraordinary engineering. Many systems had to operate inside refrigerators colder than outer space, while every component needed incredible precision. Even then, reliability remained limited. Google, IBM, and other leading laboratories regularly announced impressive milestones, proving steady progress. Yet behind every headline was the same challenge: protecting fragile qubits long enough to perform useful work. Independent researchers repeatedly pointed out that impressive demonstrations were not the same as fault-tolerant quantum computing at scale. Some experts argued that truly practical quantum computers could still be decades away. Research papers consistently highlighted noise, error correction, scalability, and hardware complexity as major hurdles. Compared with classical computers, which can perform billions of dependable operations every second, quantum systems remained astonishingly delicate. The promise was enormous, but confidence began to fade. Behind the scenes, scientists searched for better materials, smarter error correction methods, and new ways to protect fragile quantum states. Funding continued to grow, but so did skepticism. Each breakthrough answered one question while exposing three more. Investors, governments, and technology leaders kept waiting for the moment quantum computers could move beyond carefully controlled experiments into dependable everyday tools. Nobody knew whether that moment was close or still generations away. The entire field seemed trapped between breathtaking promise and stubborn reality until suddenly. Then one research team asked a completely different question, and that changed everything. Instead of building bigger quantum machines, they focused on something everyone else had been fighting for years. Instead of trying to overpower the problem with larger machines, researchers at the University of Chicago asked a different question. What if the future of quantum computing depended less on adding qubits and more on protecting the information inside them? That simple shift in thinking led them down a very different path. Working alongside collaborators from national laboratories and partner institutions, the team spent years studying how quantum information behaves under real-world conditions. Their goal wasn't just to build another impressive prototype. It was to find smarter ways to preserve fragile quantum states for longer, reduce errors, and make future quantum networks and processors far more reliable. Their work focused on improving the foundation rather than the headline number of qubits, a strategy that stood apart from much of the industry's race for scale. Progress was anything but smooth. Experiments failed. Designs were refined. Tiny improvements often required months of work, and unexpected results forced the researchers to rethink long-held assumptions. But with every setback, they learned a little more about how to control one of nature's most unpredictable systems. Then the data began telling a different story. Measurements showed quantum coherence lasting significantly longer than previous approaches had achieved under similar conditions. That meant quantum information could survive long enough to travel farther or remain useful for more complex operations, solving one of the field's most persistent bottlenecks. Independent scientists quickly recognized why the results mattered. Longer coherence isn't just another laboratory record. It creates new possibilities for connecting quantum computers, improving error correction, and building systems that can eventually operate on a much larger scale. The breakthrough didn't suddenly make quantum computing easy. Many engineering challenges remain, and researchers are careful not to claim otherwise. But it demonstrated that a different strategy could overcome limitations many believed were unavoidable. After decades of chasing the same goal from the same direction, the University of Chicago team had opened an unexpected route forward. The real surprise wasn't that it worked, it was what this breakthrough made possible. Now the question wasn't whether the discovery mattered, it was how much it could change the future. What the University of Chicago demonstrated was not a finished quantum computer that outperformed every competitor. Instead, the team showed a practical way to preserve quantum information across dramatically longer distances using existing fiber optic infrastructure, addressing one of the biggest barriers to building scalable quantum networks. Rather than chasing headline-grabbing qubit counts alone, their work strengthened the foundation that future quantum systems will depend on. That is why researchers around the world paid attention. Progress in quantum computing is often measured by isolated records, but this result tackled a problem that affects nearly every architecture. Whether companies build superconducting qubits, trapped ions, or other quantum platforms, reliable communication and stable quantum information remain essential. The breakthrough did not eliminate decoherence, but it showed that one of its consequences could be reduced in ways many considered extremely difficult. Compared with earlier milestones, the achievement represented a shift in priorities. Google and IBM have pushed quantum processors to new levels of complexity, while researchers worldwide have improved error correction and hardware performance. The University of Chicago's work complemented those advances instead of replacing them, suggesting that future success may depend on combining stronger processors with stronger quantum connections. If those pieces eventually come together, the impact could be enormous. More dependable quantum systems could accelerate artificial intelligence research, speed up drug discovery, uncover new materials, improve financial modeling, refine climate simulations, strengthen secure communications, and support next-generation supercomputers. Governments also see strategic importance because quantum technologies could influence economic competitiveness and national security for decades. The scientific community welcomed the findings with cautious optimism. Experts praised the technical achievement while emphasizing that many challenges remain before practical, fault-tolerant quantum computers become reality. Engineering complexity, manufacturing, large-scale error correction, and affordability are still major obstacles. Turning laboratory success into commercial technology will require years of collaboration between universities, industry, and government. Even so, the breakthrough changed the conversation. Instead of asking whether progress had stalled, researchers began asking how quickly these ideas could be integrated into future quantum systems. That subtle change in perspective may prove just as important as the discovery itself. Investors noticed. Startups adjusted strategies. Established companies watched closely, knowing today's academic discovery could become tomorrow's commercial advantage worldwide. But this breakthrough may not end the quantum race. It may only signal the beginning of an even bigger competition. History shows that every technological revolution creates new opportunities and new challenges. History shows that the future of quantum computing remains unwritten. The University of Chicago's breakthrough has opened a promising path, but turning laboratory success into practical quantum computers will take years of engineering, investment, and global collaboration. Universities may continue producing bold ideas, while technology companies provide the resources to scale them into real-world systems. Governments are also expected to increase funding as quantum technology becomes more important for economic growth and national security. At the same time, experts warn that powerful quantum machines could eventually threaten today's encryption, making quantum-safe security an urgent priority. Most researchers believe practical, fault-tolerant quantum computers are still years away, but every breakthrough brings that future a little closer. History often remembers the moment a race changes direction, not just the moment it begins. If one university discovery can shift the balance of the global quantum race, who do you think will build tomorrow's first truly useful quantum computer? And how could it change our everyday lives?